So far in Chapter 11, we have only been looking at the probability that an event will occur. But when we are using probabilities to make decisions in life, probabilities aren't the only factor we need to consider. Say I offer you a chance to pull a card out of a deck. If the card is a jack, you win $50. If I charge you 25 cents to play, would you take me up on it? How about if I charge you $5? $10? $25? You'd probably say yes if the charge is 25 cents, maybe even $5 or $10. Most people would say no for $25. Why? The probability of winning is always the same. Well, if you want to decide whether to play a game, make an investment, etc., you're interested not only in the probability of winning, you would also want to know the amount you would expect to gain or lose. The measurement that takes both into account is called expected value. Conceptually, expected value measures the average amount of gain or loss over the long run. Example 1. Pull one card from the deck. If the card is a jack, you win $50. If the card is not a jack, you lose $5. Find the expected value of the game. How often would we expect to win this game? Well, there's 4 jacks in the 52 card deck, so we would expect to win 4 out of every 52 times we played. We expect to lose the other 48 out of 52 times. So the probability of winning $5 is 4 out of 52, and the probability of losing $5 is 48 out of 52. I just corrected a typo down here. We can organize this information into a table. Label the columns amount and probability. Drawing this table should be the first step in expected value problems. In the rows, put all the possible outcomes of the situation. In this case, there's only 2, jack or not a jack. So in the rows, jack and not a jack. Read back through the problem again. As you come to each number, fill it into the chart. Pull one card from the deck. If the card is a jack, you win $50. Put $50 in the amount column for jack. If the card is not a jack, you lose $5. Put -5, because it's a loss, in the amount column for not a jack. The problem doesn't mention the probabilities because we can find those ourselves. There are 4 jacks in the 52 card deck, so the probability of a jack is 4 out of 52. Not a jack is the rest of the deck, 48 out of 52. For the expected value calculation, multiply each row, then add the answers together. Multiply 50 by 4 out of 52, multiply -5 by 48 out of 52 and add them together. Your book suggests doing this calculation as a single fraction with common denominator 52. This method avoids rounding until the end of the problem. The numerator is 50 times 4 minus for -5 times 48. So what's happening here is these denominators 52 have become this 52, and so if we take them out here, we end up with just this calculation for the numerator. So let's put those fractions back up here. So 50 times 4 is 200. Plus, or we could just write this as a minus, since it's negative. 5 times 48 is 240. 200 minus 240 is -40. So far we are at -40 over 52. How will we leave that answer? This answer is not a percent or a probability. Remember that expected value measures the amount of gain or loss over the long run. So the answer is an amount, usually an amount of money, but an amount of whatever amount the problem describes. In this case, it is money. So we need to round this to 2 decimal places to make the answer look like a dollar amount. So don't reduce a fraction, put it in a calculator. On our calculator, divide 40 divided by 52. Gives us 0.76923. So round it up to 0.77. Remember, it's negative, so the answer is negative $0.77. Make sure the negative is part of your answer. That's very important. This answer means that if we play this game over and over, we expect to lose, because it's negative, an average of 77 cents per game. So mathematically, this is not a good game to play, because you lose. You might choose to play it anyway because you think it's fun and you're willing to accept the risk of losing $5 to maybe win the 50. But be aware that mathematically, in the long run, you would expect to lose money even if you win once in a while. The expected value formula comes from our calculation, multiplying each row and adding the results. So the expected value, or VEV, is, well, for each row we're multiplying amount times probability, and then we add the next amount times probability. And if there were a third row, we would add that amount times probability. And we just continue for however many rows there are in the table. Anytime a problem asks for expected value, expected number, expected amount, etc., begin your work by making a table with amount and probability. Note that the probability column must always add up to 1, since it includes all possible outcomes, so it's a whole sample space. Example 2. A box contains 6 gift certificates, one for $10, two for $20, two for $50, and one for $100. For a fee of $25, you may reach in and choose a gift certificate. What is the expected value of a selection? Since there's a fee of $25 this time, even if you get lucky and pull out the $100 gift certificate, you haven't really won $100. You've really won $75, $100 minus the $25 that you paid. If there's a cost involved, we must always subtract it from the amount column. Since this is an expected value problem, we always begin by drawing the amount probability table. In the rows we put each outcome, $10 certificate, $20 certificate, $50 certificate, $100 certificate. So we're going to need more rows this time. $10 certificate, $20 certificate, $50 certificate, and $100 certificate. Even though there are two $20 certificates and two $50 certificates, we only need one row for each. We'll show that there are two of those certificates in a moment in another way. In the amount column, the $25 fee needs to be subtracted from each of the amounts. For the $10 certificate, the amount is $10 minus 25, or negative 15. For the $20 certificate, 20 minus 25 is negative 5. 50 minus 25 is 25, this time positive. 100 minus 25 is 75. For the probabilities, there are 6 certificates. That means that all the probability denominators will be 6, since our sample space is the 6 certificates. There is one $10 certificate, so that probability is 1 out of 6, or 1/6. There are two $20 certificates, so 2 out of 6. Two $50 certificates, 2 out of 6. One $100 certificate, so 1 out of 6. Now multiply each row and add the results. Negative 15 times 1/6 plus negative 5 times 2/6 plus 25 times 2/6 plus 75 times 1/6. Write this as one big fraction with common denominator 6, and the numerators will be negative 15 times 1 plus negative 5 times the numerator 2 plus 25 times 2 plus 75 times 1. So calculating negative 15 times 1 is negative 15. Then for the next we can put minus 5 times 2 is 10, and plus 25 times 2 is 100. 50. 25 times 2 is 50. Finishing that calculation, negative 15 minus 10 plus 50 plus 75 gives us 100 over 6. Remember that this answer is an amount of money, so don't reduce the fraction. Divide 100 divided by 6 is 16.66666666. So round it to 2 decimal place would be 16.67, or $16.67. This means that mathematically we expect to gain, because it's positive, an average of $16.67 per selection. So if we were to do this over and over lots of times, on average we do expect to come out ahead. In our examples so far, the amount has always been money. In example 3, we'll have a different type of amount. United Airlines is planning its staffing needs for next year. On January 1st, the FAA will inform United Airlines whether it will be granted the new routes it has requested. If the new routes are approved, United will hire 850 new employees. If the new routes are not granted, United will hire only 150 new employees. If the probability that the FAA will grant United Airlines' request is 0.25, what is the expected number of new employees to be hired by United Airlines? We're asked here for expected number. Anytime we want to find an expected amount or number, we start by drawing the amount and probability table. The rows will be new routes are approved. I'll just put routes are approved. And the new routes are not approved, or the new routes are not granted. I'll put not granted. Read back through the problem and fill in each piece of information into the table as we come to it. So United Airlines is planning its staffing needs for the next year. On January 1st, the FAA will inform United Airlines whether it will be granted the new routes it has requested. If the new routes are approved, United will hire 850 new employees. That gives me the amount for when the routes are approved, 850. If the new routes are not granted, United will hire only 150 new employees. That gives us the amount for not granted, 150. If the probability that the FAA will grant the United Airlines request is 0.25, so that's giving us the probability that the FAA will grant United Airlines request is 0.25, so they're giving us the probability that the routes are approved, 0.25. What is the expected number of new employees to be hired by United Airlines? The problem doesn't give us the probability that the routes are not approved or not granted, but we can figure that out by taking 1 minus the probability the routes are approved. That's our probability formula for not. The probability of not A is 1 minus the probability of A. So 1 minus 0.25, which equals 0.75, goes in the second probability slot. Also remember that the probability column must always add up to 1. So anytime there is one missing probability in the column, we always subtract 1 minus whatever probability or probabilities are already in the table to get the last probability. Here the probabilities are decimals, so we won't need to make a big common denominator fraction for the calculation. We'll just multiply. First row, 850 times 0.25. Then plus 150 times 0.75. $850 times 0.25 is 212.5 plus 150 times 0.75 is 112.5, and that equals, see, we've already got the 112.5, so let's just add the first number to 12.5, and that gives us 325. The answer for expected value is always an amount. This time, that's not an amount of money, it's an amount of employees. Whatever amount is described in the problem, whether it's money or people or whatever, that's what you get for an answer. So this answer, 325, is the expected number of employees, since that's the amount discussed in the problem. This answer is harder to interpret as a long-run average since it's probably only happening once. We could say if the airline is in expansion mode and will be doing this several years in a row, then we expect the number of employees hired to be an average of 325 per year. Example 4 describes a raffle where a lot of tickets are sold and one or a few big prizes are given away in a drawing. Raffle examples are very common expected value problems, so you can expect to see one on your quiz and or your exam. Example 4, 10,000 raffle tickets are sold for $5 each. Prizes will be awarded, one for $5,000, two for $3,000, and 10 for $1,000. Sam purchases one of these tickets. Find the expected value of a ticket. Whenever they ask you for expected value, draw the table. The rows will be the different prizes that can be won. So we're going to need some more rows here, it looks like. The rows will be the different prizes that can be won, so we could win the $5,000 prize, one of the $3,000 prizes, or one of the $1,000 prizes. But there's actually one more row that we need for this. There's one more possibility. In fact, it's by far the most likely outcome if you buy a ticket. So let's add one more row. Most tickets will be losing tickets. Those have to be included as a row in the chart. For the amount column, note that tickets cost $5 each. So that $5 cost will have to be subtracted from each of these prize amounts. So subtract the $5 cost. For the $5,000 prize, the amount would be $5,000 minus the $5 cost, so $49.95. For the $3,000 prize, $3,000 minus 5 would be $29.95. 1,000 minus 5, $9.95. Then the losing tickets, those tickets win no prize money, but they paid the $5 cost, so the loser amount would be negative $5. Now the probability column. What is the probability that if you buy a ticket, you will win the $5,000 prize? Well, there were 10,000 tickets sold and only one $5,000 winner. So the probability is 1 out of 10,000. There will be two $3,000 prizes awarded, so the probability of winning one of those is 2 out of 10,000. $10,000 prizes means the probability is 10 out of 10,000. All the rest of the tickets are losers. Well, how many tickets won some amount of money. One $1,000 prize plus two $3,000 prizes plus 10 $1,000 prizes makes 1 plus 2 plus 10 makes 13 winning tickets. All the rest of the 10,000 tickets are losers. So 10,000 minus 13 makes 9,987 losing tickets. So the last probability is 9,987 over 10,000. It's a common mistake in raffle problems to forget to include the losing tickets. If you didn't originally have the last row in your chart, you should know that something's wrong because the probability column always has to add up to 1. Without that row, we're not even close. So looking where this information in the table or in the problem went into the table, 10,000 raffle tickets are sold became the denominator of the probability fractions. The total number of tickets is the denominator of the probability. Are sold for $5 each. This cost is subtracted from each of the amounts. One for $5,000. The number of each type of ticket is the numerator of the probability fraction. 2 for 3,000, the numerator is 2. 10 for 1,000, numerator is 10. And the last numerator for losing tickets is the total number of tickets, 10,000, minus the other numerators. So 10,000 minus 1 minus 2 minus 10, which is 13, equals 9,987. This makes the probability column add up to 1. This calculation will be set up as one big fraction with common denominator 10,000. So let's try to just go ahead and go right to the big fraction right off the bat. In the numerator of the big fraction, we'll have the amount times the numerator of the probability, 49.95 times 1, plus 29.95 times 2, plus 9.95 times 10, and then minus, because it's negative, minus 5 times 99.87. So calculating each of those products, we get 49.95 times 1 is 49.95 plus 29.95 times 2 is 59.90 plus 9.95 times 10. I shouldn't need a calculator for that. That's 9,950. And then, oh, actually minus, because the next one's negative, 5 times 99.87 is 49,935. So 49.95 plus 59.90 plus 99.50 minus 49,935 is negative 29,000 over 10,000. And divide we get negative 2.9. The amount type in the problem this time is again money, so that would be negative $2.90. Make sure you get the negative as part of the answer. That's very important because that's what tells us it's a loss. This means if we averaged out the money each ticket won or lost, including all the prize winners and all the losers, the average amount would be a loss of $2.90 per ticket. So to recap, in raffle problems, the probability denominator, the 10,000, well, that was the total number of tickets sold. The probability numerator of each row is the number of tickets of that prize amount. The amount in the amount column is the prize amount minus the cost. And be sure to include a row for the losing tickets.